Hi all, welcome to part 9 on combinational circuits. See, we were discussing many different examples of combinational circuit design, particularly the adder circuit, half adder, full adder, ripple carry adder, carry look ahead adder, many things we saw already, right? And also that code converter. Now it's time for us to see something called a multiplier, but actually in your syllabus this is not directly given, but I just thought of explaining this because it's a very simple circuit, right? So once you understand how that addition and subtraction, add a subtractor circuit also we saw, right? Is done, how this multiplication can be done. It's a very small idea, right? And you basically know how this multiplication is done, right? So given 2, so here it's shown the multiplication of two bit numbers. Say the first number is your something like I'm going to multiply a number b, which is a 2-bit number. Let me denote the bits like b0, b1, and with another number a, let the bits be a0 and a1, like that. So just 2-bit number multiplication. This you can generalize for any bigger number, right? So for an n-bit number you can generalize a concept. So that is why we are just starting with the 2-bit number multiplication process. And you know, when you multiply, so first what you will do is you will take this a0 and you multiply it with the b0. You will get this term a0 b0, that multiplication, that AND operation, right? So then you will multiply this a0 with the b1, you will get this term, right? a0 b1. Now this is the first partial product you are getting, right? Then you will add this partial product with the second partial product. So how you are getting second partial product? So to get the second partial product, this a1 you have to take and you have to multiply it with the b0. You will get this a1 b0. Then a1 you will multiply with the b1, you will get a1 b1. So like that you will get the second partial product. Now these two things you will add. The normal addition process, you will get to c0, c1, c2, c3 as a final result, right? So this is the final carry you are getting. So that's all. So the normal half adder or full adder circuit you can make use of, but you know, for adding the partial product. So now the generation of the partial product is what matters, right? Yeah. See, that's all. So first you have to generate the partial product a0 b0. So what you are doing, this a0, first you are taking this bit a0, then you are multiplying it with both b0 and b1. So a common line it's is shown, like from a0 you have a common line, and that is given to both AND gate. The first AND gate will multiply it with the b0, you will get a0 b0, and the second this particular AND gate will multiply the same a0 with the b1, you will get a0 b1. See these two terms, right? So that is what is happening. So that the multiplication process is done by AND gate. Similarly, this a1 you take the second bit of the multiplier, right? That's a1 you multiply. So a1 is taken commonly given to 2 AND gate. The first the least significant AND gate will multiply it with the b0, you will get a1 b0, and here you will get a1 b1. So that's all. Now finally this partial product are to be added, right? So first this this particular partial product you don't have to do any addition, you can simply take it directly in the final answer. So we are directly taking it in the final answer. Now here there is an addition. So in this particular case of 2-bit multiplication, there is only a single addition, right? So it's a0 b1. I mean here you are getting a0 b1, right? This a0 b1 is to be added with the let me write it here. So this line, so here you are getting a0 b1, and that is to be added with this a1 b0. So here you are getting a1 b0. So this one is your a1 b0, and these two things you are adding. You can just use a half adder because it's the first level of addition. There is no carry at all because this thing you are directly taking, right? So it's enough to use a half adder. Now this half adder will generate a sum, and that is the next bit of your result, and a carry, and that carry you will get a carry from here, right? So after this sum there will be a carry, and that carry is being added with the next bit of the partial product, second partial product. So the second partial product is something like a1 b1, and that you are adding with this particular carry, you will get the c2, and the final carry will be your c3. Hope the circuit is clear, right? So normal multiplication you are done with the help of an AND gate. Then this addition here, half adder is enough because 3-bit addition is not happening. If some carry is coming from here to here, then you might use a full adder here. So you can see that here only just 2 bits addition is happening maximum. That is why you are using half adder in case of 2-bit multiplication. But when you generalize it to say a 4-bit so this is something a general case. A 4-bit number is being multiplied by a 3-bit binary number. So it is something like this. I have to multiply. So this is my multiplicand multiplier, right? Something like that. Multiplicand is like b, say b3, b2, b1, b0. So the b0, this is a 4-bit number. So that is being multiplied by a 3-bit number, say A, that is A2, A1, A0. Only 3 bits are there. Now same procedure you have to do. First you take this, you know the multiplication procedure, right? So B3, B2, B1, B0. When you multiply it with A2, A1, A0. So first you have to take this A0, multiply it with B0, B1, B2, B3. You will get the first partial product. So that is what is happening. This A0 is taken. This A0 is taken. First you have to multiply this A0 with see A0 is coming everywhere. So from here you will get what? A0. B0 you will get. So from here this is the first term, A0, B0. Then A0 is multiplied with B1. So here you will get A0, B1 or B1 A0. Anyways you can do this because AND is also commutative, right? So here you will get A0, B1. Then this same A0 with B2, right? You will get the next bit of the first partial product, that is A0, B2, finally A0, B3. So like that you will get the first partial product. So here you will get A0, B3. Yeah, that's all. Now once you get it, what is the next thing you have to do? So you take the next bit. So that is initially you taken this A0, next you have to take this A1, right? So A1 is taken, and you are multiplying the same A1 with the B0, B1, B2, B3, right? So from here you will get A1, B0. From here you will get same A1, B1, then A1, B2, then A1, B3. So that's all. So these are all the bits like A1, B0, A1, B2, sorry, B1. 4 bits are coming, right? A1, B2, and finally A1, B3. So like that. Now finally one more step remains. What is that? You just take this A2 and you can multiply this A2 with all these 4 bits like A2. So then you will write like this, right? A2, B0, A2, B1, then A2, B2, and finally A2, B3, like that. So finally you have to add all those things together. So here you are getting the same A2 is coming, A2, B0, A2, B1, A2, B2, and finally A2, B3. So like that. Now you have to perform the addition of the partial product, right? So what is happening, this one you can take as it is in the final answer, right? You are just taking this as it is as the first bit of the result, the C0 you are taking like this, right? You can see that. Now what about the C1? So here there is an addition, right? So when you are adding, one second. Now see how further things are implemented. So this one you taken directly, so that is over. Now you have to add this bit with this bit, this one with this one, this one with this one, and finally here there is nothing. So let me, if there is nobody to add, I can take like that. So right now you can observe here. So here actually you are trying to add 2 4-bit numbers together, right? So this is actually, so first you have to add these two partial product, then with that result you have to add this partial product. So that is the final answer. So here you can see a 4-bit addition, right? So these 2 bits you have to add, then these 2 bits, then these 2 bits, then these 2 bits, and here you can use a half adder, then 3 full adders are enough, or you can use 4 full adders. So finally if you are having a 4-bit ripple carry adder or 4-bit carry look ahead adder, whatever it is, so if you are having a 4-bit adder, you can feed these bits. I mean the first number you can feed like so the most significant bit you can feed as 0, see, and the remaining bits like A0, B3, see, A0, B3, A0, B2, and A0, B1. So like that you are given the first input, and the second input is like this A1, B3, A1, B2, like these bits, right? So finally these two things are being added. So what is happening? So here these 2 bits are at, these 2 bits are at, these 2 bits are, finally you will get a 4-bit number, right? So 4-bit number, and out of that this least significant position, actually you will get a 5-bit as a result. When you are adding 2 4-bit numbers, when you add 2 4-bit number, right, so actually you are adding this one, this one, this one, this one, and finally there is a carry also. So final result is a 5-bit result. So out of that 5-bit, the least significant bit, that is the result of A0 B1 plus A1 B1, you are directly taking as C1. I mean this particular addition is happening here, and the remaining 5 bits, I mean this bit, this bit, this bit, and one more the final carry. So those 4 bits you are applying to the second adder, where one of the input is the output of this one, right, and another input. I hope it is clear. So when you are adding these 2 bits, you will get something like S0, S1, S2, S3, S4. S4 is the final carry generated from the 4-bit adder. And this S0 you are taking directly as your C1, and the remaining 4 bits is the first input of the second 4-bit adder. Here you can use a normal triple carry order, carry lookup adder, whatever it is, according to the requirement you are having, right? Whether it is speed or space and all. So that about it. Now the second number, as it is you are applying, I mean these 4 bits you are applying. And then you are adding and you are getting here sum is being generated. Now with that sum you are adding this, you will get this C2, right? Similarly here you will get C3, C4, C5, and finally there is a final carry, that is your C6. So like that you will get the final answer, say 0 to 6, 7-bit result you are getting, right? So because a 4-bit number you are multiplied with a 3-bit number, that is why the result is like 7-bit. So that about it. Hope the circuit is clear, right? So if you have any further doubt and all, you can ask, but anyways this is not something mentioned directly in your syllabus. Just for the sake of completeness I thought of taking this also. So next part onwards we will move on to what are all the things that you are supposed to know from the syllabus point of view. So this is something I taken extra because as we already seen adder and subtractor, I thought of explaining a multiplier circuit also, and you can generalize it. Now I hope you got an idea of how this n-bit multiplication can happen. So like that you can when n is large, like suppose you have to multiply to 8-bit number and all, 3 or 4, 8-bit number is being multiplied with another 8-bit number or a 4-bit number, and that case you can see that the partial products are of some 8-bit, 8-bit, 8-bit size, right? So to add them you can use an 8-bit adder. Suppose you are having only 4-bit adder available with you, you can form an 8-bit adder using 2 4-bit adder, and you can feed this input. So like that you can generalize any level, but it is slightly a complex circuit because the partial product generation, their addition, everything you have to take care. But this is simple, like you partial product generation is simply this AND operation is generating each bit of the partial product, then the addition you have to do properly. That's all. Yeah, thanks for watching, and any doubt you can ask during our discussion class. Yeah.